Alright, so welcome to our senior design presentation for the fall of 2017. My name is Jonathan Loray. My teammates are Jason Soto and Christopher Perez. Our project is an invention we call the Bella Umbrella, and it provides weather protection for two-wheel drivers. So a big problem we have in the world today is that a lot of people cannot afford automobiles or anything that covers the whole body while driving. So as a result, you'll need to resort to buying scooters, bikes, or motorcycles, and unfortunately these mediums of transportation are very dangerous, expose you to any element of weather, can even blind you from the sun. And unfortunately, the solutions we have right now to solve these issues are either a little too cumbersome, expensive, or they don't fully do the job. So our solution is we invented a canopy that opens and closes, it's retractable and deployable. It has a clear vinyl to provide maximum vision with rain-X applied so that the rain will simply wash away. It's lightweight, it's durable, and it's going to be essentially affordable for the most part when it reaches mass manufacturing. So here are some of the solutions that we currently have to solve this problem. First, you're going to need to buy a scooter, about $800 to $1,000, 150cc, 100cc scooter or moped. Currently we have a tarp or a poncho to help protect you. It's not too effective. You're going to have to pull over the side of the road after you get wet, apply it, put it on, but then you're already soaking wet. It's very dangerous. There's a makeshift umbrella for about $70 you can buy in China. It's not very effective, not too aerodynamic, it tends to break. And a little more expensive solution, we have another option in China. It's called the glass awning, to the top left here, which basically needs to be bolted down to a specific model of motorcycle, and it's a big glass fixture. It has a little windshield wiper at the top. We also have the motor car, more popular in India, which is a full body encompassment, but you need to buy everything together for $1,100. So if you'd like to buy maybe another scooter, you can't just simply move it to the other model you like. And probably the most expensive option we have right now on a two-wheeler is a BMW C1, costs about $5,000. Of course, it's incorporated in the design. You can't buy another scooter and then get the same effect, essentially. So the first design alternative we came up with was a pantograph-like design. It compresses very nicely in the front and covers the majority of the back part while covering the sides of the user. However, the mechanism is pretty complicated. It would break very easily. It tends to obstruct the user way too much when it deploys, as it would have a bit of a slow deployment time, and obstructs lights a little bit. And the second design we have is a more telescopic feature, which would have see-through plastic fronts, and it would be inserted into these little rectangular slots, and unfortunately make a little too much weight for the front, creating a bit of an imbalance for the driver. A bit of a difficult to deploy, and it does not cover the sides of the user, so you'll still get wet if there's a bit of wind in the rain. The design we ended up choosing was more of a single joint design, full body canopy. It is the largest of all designs, so it covers the most. And during testing, you'll see later, it does in fact get the user completely dry. It's aerodynamic. The thing is, it's not as compact as other designs, and exiting the vehicle is a little trickier.
Here are the standards that we use for this project. For this first set of standards that we use is the Engineering Code of Ethics provided by the National Society of Professional Engineers. We did this to make sure that all of our figures and reported values were going to be accurate and correctly represented. For standard industrial tooling and materials, we use ANSI grade steel for steel parts, and for non-steel materials, we use the ATSM catalogs. For the custom parts of this project, which include the mount and the joint, we had to create engineering drawings for them. The standards that we use for this are the ANSI format, and we use the English units of measurement. The federal standards were perhaps the most important part of this project, considering that transportation is a very highly regulated field. Basically, we use the CFR 49 codes in order to show that this product can withstand any impact from a collision. These are the materials that we would have used for the ideal prototype. Basically, due to constraints, it wasn't exactly built to specs, but we would have used T6, 6061 aluminum and stainless steel for the canopy mount and joint. We would use 100% polyester and vinyl fabric for the canopy, and we would use nylon with rubber inside of it for the restricting belt. For global design considerations, we wanted to make sure that it had a mounting mechanism that would allow it to fit on 50% of scooters and as well as a majority of other vehicles. We also wanted to make sure to collaborate with local governments to see if we can create this without offending any religion or society. We also wanted it to protect from other weather conditions such as intense sun and snow. But most importantly, we wanted this to be user-friendly with a easy-to-understand user's manual. What we wanted to do with this project is make a scooter comparable to the automobile in the market. This will create some competition between the two if this is fully implemented.
All right. So after taking into account our manufacturing capabilities and our budget, we decided upon this as our final design for the prototype. This design can be broken up into three main sections. There is a canopy, which is contained by the ribs and the vinyl coating. We have the joint, which is the main mechanism that allows everything to function, and we have the mount, which is the method of attachment to the vehicle. To begin our simulation part, we decided to figure out how much forces this device would experience while traveling on the road. To do this, we used a vehicle speed of 50 miles per hour, as this is typical for 150cc scooters, and a wind speed of 34 miles per hour, as this is also typical for thunderstorms. We ran several types of simulations. As you can see, we have 0, 90, 45, and 180 degrees. This is the alignment of wind with the direction of motion of the vehicle, 0 degrees being headwind with the vehicle, and 180 degrees being tailwind of the vehicle. After running all these simulations, we normally found that 0 and 90 degrees produce the largest forces. Here we have the 0 degree flow simulation. This gives us the forces acting upon the canopy. As you can see, there is a frontal force of 48.1 pounds, and you can see the pressure distribution here on the picture. Now, the 90 degree simulation was the main focal point of this project because this is the simulation that generated the largest stresses and the largest forces everywhere. This is due to the large sideward surface area of the canopy and its relatively low angle. This resulted in a sideways force of 145.2 pounds, which is very notable. After obtaining the forces, we decided to run stress simulations and basically iterate geometry and materials until we found a suitable design that satisfied our factor of safety and basically weight and displacement criteria. We decided to simplify the simulations by not including any fabric, as fabric takes extremely long time to simulate, and also by simplifying the whole model and using as few pieces as possible, gradually building up until we made sure all the pieces survived testing. Here we see the 90 degree stress simulations. 90 degrees used because, again, this one is the one that produced the largest forces. Here we have the rib, and we iterated dimensions about a 1 inch for the front rib in diameter and a thickness of 0.125 inches. Now, we have a factor of safety of 1.027 here, but that's okay because this part is actually reinforced by the rest of the assembly. And as we'll see in the next simulation, when it is combined with the joint, which is here the rib plate, the entire assembly actually goes up to a factor of safety of 2.27. Right? So now that we simulated the canopy and the joint, we move on to simulating a larger assembly, which includes the mount. And by running this assembly, we iterated until we got a factor of safety of 1.8. However, we had to change the ideal material from stainless steel to 1045 cold rolled, as this was provided enough strength to support the entire assembly. After designing the system and figuring out all the geometry we're going to use and all the materials and basically thicknesses of everything, we decided to begin finding out the main components, especially the gas spring, that we could use to power the mechanism. There are three behaviors we were aiming from this mechanism. First of all, self-deployment, easily collapsible, and self-storing. To do this, we ran moment simulations and used a canopy weight of 10 pounds, moment arm of 32 inches to the centroid, and a starting angle of 25 degrees, which is where it rests when it is in the downward position. After running the simulations, the calculations actually, we got this curve here, which is a setting force, which is the hand force required by a person to close it. It starts up pretty high at around 12 pounds and goes down to 0 pounds when you latch it to the ground. This mechanism also is the self-storing motion, but at 35 degrees, meaning that you'd have to lift it from 25 to 35 degrees for the entire mechanism to stow away. But it would activate at 25 degrees, which is the deployment, meaning that it would open up. Here we have the gas spring force graph. This one indicates in red the force of the gas spring, and in blue the force required to open the mechanism. And you can see the intersection point is when it can open up, and that's approximately at 35 degrees.
There were many manufacturing techniques that we used to make the prototype. The mount and the joint were outsourced to manufacturing companies, mainly water jet companies, to make them because we wanted them to be very precise. However, we did the rids for the canopy ourselves. This is a SolidWorks simulation of how it actually assembles. These are the prototype parts list. There were 3 main components for it, and it was the joint, the mount, and the canopy. The prototype cost about $600 to make, which was about double our initial estimate. However, this cost is a lowball considering that it would have cost a lot more had we had our manufacturing company do the bending or the welding. It would have cost about $1,500. Now, the main changes we have on this design were we used 1 full joint instead of 2. That's why it's curving like that. For the major changes to the canopy, we decided to use multiple coupled joints instead of 1 huge long pipe due to ease of transportation, and we changed the material from aluminum to EMT pipe. Unfortunately, these changes did indeed impact the testing, as you will see.
So we were quite surprised during our testing. For one, it travels quite nicely down the road. I expected it to be a bit more of an imbalance, maybe a little more wiggling, but it actually flows quite nicely, about 45 miles per hour. A little more than that, you will get a little bit of resistance. However, strong winds directly from the left or right, as discussed earlier in the simulations, will create a bit of an imbalance to the point where you might have to pull over to the side of the road. That's definitely something we need to look into. Furthermore, is a video of us opening, closing, and stowing away the canopy just to show you how it works. Essentially, of course, due to the material change from aluminum to the steel, the material now is a bit too heavy to operate automatically, and thus we had to have a little more of a manual operation. If made of aluminum, it would open automatically via the switches on the side here, which act as somewhat of pike brakes with a spring mechanism down there which locks in place, holding it, and then it will be able to open on its own, stow away on its own, or close on its own. And the seat itself, being that it's made of a water jet, just flat out steel, it's very rigid, it's not too ergonomic. So it's a little uncomfortable, but you know, a basic cushion would fix that issue. Another issue that was a bit of a surprise to us was that the lights from the scooter actually ended up reflecting off the canopy themselves and created a bit of a blinding effect, if you will. You can still see fairly well. However, it does create a bit of a distraction as well. If a vehicle is behind you and they turn their high beams on, it will also end up reflecting off the vinyl, making a little more of a uncomfortable blinding effect. Most important simulation, of course, was the rain. How does this hold up in the rain? Well, we applied Rain-X to the front sheet of the canopy only, since that's the most important one. That's where you need to see when you're driving. And it's holding up pretty well, as you can see, even though we're putting a lot of pressure, a lot of variance in the way the water is hitting the canopy. You can see quite clearly through it, even when the canopy is a bit foggy from certain weather conditions, or if it's a bit sunny, that can act as a bit of a shade so that it doesn't blind you completely. But we were quite surprised with this as well, as we were initially thinking of putting windshield wipers. However, looking at videos online of how Rain-X works, as you can see, it does the job just fine. So for our future work, we'd like to implement a string of LED lights along perhaps the back end of the canopy, so that as opposed to a driver from the back at night seeing only the backlight of a scooter, they'll now be able to see a nice giant ring, which makes you a lot more visible at night, so people will be less inclined to ram into you. And inner canopy padding as well, so that in case the moment of an accident, the entire canopy will act sort of like a giant baseball glove and catch you and perhaps pad the fall, so that instead of being hit from the back and you being skid across the street, it'll probably catch you, make the journey a little softer for you and easier, maybe even save your life as well. And we're also thinking of adding some little slits at the front for temperature regulation that will be open or closable, that in case you want a little bit of cool air to come in, you can open those up. More flexible seat mount, of course, make it a little more ergonomic so they can accommodate not only more scooters, but be a little more comfortable to sit on as well. And we're thinking of implementing a rotating joint to this, which will fix the light reflection problem, so that you can angle the entire thing as it's open to a different degree, so that the light will shine through and you won't have as much reflecting, and you'll still get the same amount of coverage. And we're thinking of a slightly tinted roof, so in case it's really bright sun, you're not going to be blinded, and it'll provide that nice amount of shade for you. And we'll be taking questions now.
Are you going to fold it up? Will it fold up?
Jason, do you want to open it up? Okay, so you can see. It looks cooler when it's deployed, believe me.
You guys, could you?
Wait, is someone gonna get actually live?
Actually, yeah, like it should, let's go.
Yeah, so as you can see, because of, again, the fact that this is made of steel, it doesn't open on its own. However, we did the simulations, and if it was made of aluminum, it would just open up nice on its own, so it's having to manually operate.
So I have a question and an observation. My question is, actually my observation is, it seems you did the water repeal test for the Rain-X, but something you might want to include on your future work is actually testing it, because I mean, the work itself and the structure is very impressive, but is it a solution?
Right.
Is it going to repeal the water coming below you, or is it just gonna protect your torso from not getting wet, everything else is getting wet?
Right. If I could interject just a moment, we did test it in very light rain, and we drove about 40, 45, and we were pretty much completely dry. The only time I felt a little bit of soakiness was when the hose was deployed right at the front. Bit of my shoe was a little wet, but other than that, it's pretty engulfing for the effect of the kids. It keeps you pretty dry for them.
And my question is, I believe you mentioned you wanted to target with either 50% or 75% of all models. Is there anything you did to prove this?
So we essentially did a lot of research in just how seats look and how scooters look in general. This is a pretty common standard scooter you find very, very cheap, $700, $800, $900 model, 150 cc, nothing too fancy. And a lot of seats at most maybe will curve up a little more, or maybe a little more custom bikes will be a little more geometrically different. But for the most part, you have like this nice flat, slender bottom, which is why we didn't focus too much on the shape of that seat mount. But when you start getting into motorcycle territory, you're going to have a lot more differences in size and shape and geometry. So we decided to only focus on scooters, and then perhaps potentially work on bikes as well, if it fits nicely on the seat and ties down to it.
Last observation for your future work is maybe try and understand how you're going to address one of the main reasons people get motorcycles, which is lane splitting. With that, you're going to have, rather than splitting and getting to your destination faster, you're going to have to wait in the rain or just wait in the sun.
Right.
So that's another.
Right, that's a good observation. It is quite wide, but if it wasn't this wide, it wouldn't be able to, fit over the front, fit over the back. Just a little mishap of this design is that it needs to go over the front and the back, and because of that, we want to make it nice and wide. If I'm not mistaken, certain motorcycles aren't allowed to go in between lanes like that. That can be illegal in certain states.
So it is illegal in all states except California.
Okay.
That doesn't, but that's in the U.S.
Right.
around the world,
Of
which
course.
I think you're marketing this
Right.
around the world, those regulations aren't really
Right.
upheld, or people don't follow them. So that's just something else to consider.
Definitely, definitely.
Couple questions. First thing, initially you're talking about some standards tied to collisions and impact. How did you use those standards for this design?
Due to the nature of this design being very jerry-rigged and fragile, we weren't actually able to test having an impact on it, because it would have damaged this design. So we mention it for the report.
But you don't actually use it. is what
We
you-
don't actually use it.
Okay, that's the first question. Second one, you said it was designed for 50 mile an hour with 35 mile an hour side winds. Would that wheel be off the ground if I was riding this thing at 50 miles an hour and I saw 35 mile an hour side winds?
It would not be off the ground. The forces that are generated are not enough to lift the entire vehicle up. At most, which is the most serious concern, is the 145 pound force pushing you to the side. That one's
So you would-
dangerous. Yes, because
You change lanes. is what-
Yes, exactly. And that was the one that we've been thinking about other solutions to work around that problem. But as of right now, that's the main flaw of this design.
Okay, then the last one I wanted to talk about was, which was a good catch on the glare issue. A lot of convertibles have dark cloth. That's probably why. And you could very easily design this with just the front segment being transparent and the rest of it.
Yeah. For the tinting purposes of the roof, we would also consider for the front as well, just so you wouldn't get that nasty glare effect. But mainly we were thinking of the tint
Put
for
it back
sun
on here, so
protection.
it would
Right.
actually be dark.
Right. Exactly. That
protect
way
the glare on the
get-
front.
Right. Exactly.
Okay, thank you.
Thank you very much
Thank
for
you very
having
much.
us.